Okay, so hello everyone. I'm Pedro Mendes. I'm one of the developers of COPASI. Stefan Hoops is the other one here in the tutorial. He will talk, I think, on Wednesday. So I'm just going to show a very couple of slides, very brief about COPASI, and I'm not going to do a tutorial on entering models on the very basic functions. Those you can find online on video. So I hope that the people who are at the more beginner level, that they will make use of that. I will also mention a couple of other options for those people. Before that, as I mentioned earlier on, if you didn't hear it, there is a latest version of COPASI, a snapshot as we call it. It's actually still, it's not a fully released version. It will gain a few more features, a few more bug corrections, and it will be done. But you can, if you want to install it, it's on the shared drive, which I can show you here. There's a folder called COPASI download. And if you go there, there's these three versions. The three versions are, of course, DMG is for the Macs, Linux is for Linux, and Windows is for Windows. So whichever platform you have, you would run this the same way, install them the same way you installed COPASI previously. If you don't want, if you have the latest release and you just want to use that, that's fine too. There's one or two things that unfortunately are a bug in the GUI, in the front end. There's some tables that are not being redone properly, and that sometimes unfortunately leads to a crash. But I hope that you will not get to that. So as an introduction, I mentioned COPASI is basically a temporal simulator. It doesn't do the spatial domain, so all of this part about diffusion is not included in COPASI, but you can have an arbitrary number of compartments. So it can be compartmental, and the temporal part can be done with differential equations, so ODEs. It can also be done with stochastic differential equations and the Gillespie stochastic algorithm. I'll talk about those tomorrow. And then there's a number of different analysis methods. That's just the paper which we ask you to reference when you publish something using COPASI, just so that, well, at least that we find out that you used it. So if I can show you one thing on COPASI's website, copasi.org, we do track all the papers that use COPASI in their research. If you click here on the research tab, this actually shows you a list of all the papers that we can find that use COPASI. And that includes also PhD theses and master theses, etc., which happy to say there's about over 100 per year, or at least last year was already over 100. So here you see this big list. It's a very big page. These are all papers published that use COPASI, and they're not just referencing COPASI, they actually use COPASI. We're going to use a couple of these, or at least one of them. They're classified by areas, so if you click on the area, you then get a list of just those that are from that field. So in this case, this would be cell biology. They all have a link which will lead you to the site for the journal paper, so you can actually get to the paper quickly. So these are all papers that have used COPASI that is useful, maybe useful for you to find something that other researchers have used in your area, and maybe you can get to know how they use COPASI, and you can learn from that. That could also give you a model to start your next development of your model. You could start from somebody else's model. So if you cite the software, we will find you automatically eventually, and you will get listed. If you don't cite, then we probably will not find you. Now, for the beginners, I suggest reading this chapter. This is a chapter in the book, and it is a step-by-step tutorial of COPASI. It has the various, particularly the most basic features of COPASI, and it basically tells you how to build a model from scratch, how to set up a parameter estimation, how to do sensitivity analysis. And you can follow this chapter. In case you don't have access to it, it is also in the folder, which I already closed the window, which I need to open again. But it's there in the folder. So now I need to go to shared. Under my name. Oh, this is not the one. I will get to that in a moment. But it is there under my name. There's the link to the paper. So you can read this offline, particularly those that don't have a project, and you can go step by step trying to do the examples there. Okay, so finally, I will point out that there is an online user forum for COPASI. You can ask questions. Some of us might be able to answer the questions. Also, some other users might be able to answer your questions. It is a good way to discuss issues in COPASI or how to do things, etc. So I would suggest to ask questions there. Of course, you can ask questions directly to us by email, but if you ask them here, then you get other people to share, you know, the answers. You can see the answers to questions that you might have had yourself. So I am going to move on to start COPASI. Zoom is not letting me minimize things here. So what I'm going to do is I'm going to start COPASI. I'm going to start the version that I mentioned, the new one. And here it is. This is the front end. You have basically all the features that you access are here on the right. And then whenever you click one of those, you'll get the appropriate pane on the right here updating. That's very typical software. Before I load even any model, I'm going to show you how you can change the font size because I think it's useful for you. This might be too small a font. So here I'm going to just increase the font size. In this case, 11 points should be good already. So now you see bigger font size. So that's very useful for our demonstrations. I find out myself that it's also useful when I'm moving things, say on my laptop to the desktop. I want different font sizes, etc. So I'm going to try and focus on features of COPASI that are that I want to highlight. Some of them are things that you don't know, or some even experienced users have not noticed them. So I'm going to try and highlight those rather than going through step-by-step building a model. So I'm going to load models rather than create them. In that chapter, you have a description of how to create models. So you can go through that if you're a beginner. There's also one of the video tutorials also explains that. So one of the features that is not very well known yet about COPASI is that it loads files also from the internet. You can open files from a URL. And I'm going to do that to load a file directly from biomodels. Before I even do that, I should just point out in following up from Virtual Cell that COPASI is not a database connected application. It is actually a standalone program. You install it on your computer and you're going to run your applications on your computer. There are versions of COPASI running on the cloud. We don't have one currently set up, but we're going to do that very soon using our CCAM servers. That is called Cloud COPASI. In that case, you could submit jobs to a larger server that then can run them. And this is for some jobs that would be, of course, very useful. But by and large, everything in normal COPASI, you run on your computer. So in this case, I want to open a model from the biomodels database. And it is a model that used COPASI. It's actually one of those that are on the list, which I will show in a second. So I can search and I know the author name. So it's actually this paper, understanding the regulation of aspartate metabolism using a model based on measured kinetic parameters, that appeared in Molecular Systems Biology in 2009. It's actually a paper on plant metabolism, but it is useful in this case as an example. So you could go and get the paper. If you press here on link, you'll see other ways of finding this paper. Now, I know beforehand because I searched biomodels, so I know that this exists in biomodels, and I know that this is model number 212, so 212. That's key to loading it. So what you do is you go to File, and you do Open from URL, and when you do that, COPASI shows you as a default, the URL is for biomodels, and it actually has the first biomodel, biomodel 1. That's what it would have by default. Now I want biomodel 212. So what I have to do is delete the last 3 digits and type 212. The thing about biomodel identifiers is that they always have this size. So if you wanted model number 10, you would just delete 1 digit and type 10. If you want model 212, you have to delete 3 and do 212. So that's the model I'm going to load. I don't know if you're following. If you are, this is what you would type. You can probably just also watch. I'm going to stop and just ask if there's any questions. I'm not sure I can see, where do I see the participants to check whether there's any hand raised?
I have a quick question.
Okay, go ahead.
So I think you may have already mentioned this, but I missed it. So the biomodels, people can just directly get them from the COPASI website, or?
No, the biomodels database is a database that they have their own project. What they do is they have a number of curators, and they do create models that are published in papers, and they also reproduce them, and they try to reproduce at least one of the figures in the paper, and they annotate everything, as you will see in a moment. That's why one of the reasons why I'm going to load from there. You as a publisher, as an author, you can also submit your models to biomodels, and that's a good practice when you submit your paper to review, to have the model submitted to biomodels, just like you would submit a sequence from if you're doing sequencing, or a protein structure if you're doing X-ray structure of proteins. So you submit your model, they can keep it confidential if you need to until the publication, or you can even make it immediately available if you want to. They will then, first it goes into an unannotated section. Later on, once they go through it and they verify that it reproduces your paper, they put it into the curated section. And this one comes from the curated section.
Thank you.
I should add that the virtual cell, because it does have that database, we have put all of the compatible biomodel.net models into that database as well. So you can search for them in virtual cell too.
Okay, so just moving forward. So I've just typed here, this is the URL. Hopefully that works. I will press OK. And now COPASI will go and fetch it from the biomodel server and it loaded. So here it is. This is what it appears. This here is a section of comments that were written by, I guess, the biomodels curators, or maybe the authors, or a combination of the two. I don't know. The model tells you some basic, this front page tells you some basic things about the model, like the units of time, the units of volume, of area, of length, and the unit for quantity. That's the number of particles, mass. In this case, it's micromole. Sorry. You also see Avogadro's number here. That is quite important because Avogadro's number is how we convert moles into particle numbers, and COPASI actually does all of the calculations in particle numbers. So internally, everything is converted to particle numbers. This thing about stochastic correction, you can ignore it. We'll talk about it tomorrow or the next day when we talk about stochastic simulations. Now, COPASI shows the model in two ways: the biochemical view, which is very equivalent to what in virtual cell it's called biological model, the biomodel. But it also shows you a mathematical view where you can see equations. So I'm going to show you here the biochemical part first, which is actually where you can edit the model. The mathematical is only a view. You cannot enter things directly there. You can only enter things directly in the biochemical part. The mathematical is made automatically. So it shows compartments. There's only one compartment here. It's a chloroplast. I can show you. It shows the compartment name. They just called it CHL. Says it's a 3D compartment. It has a fixed volume. The volume is, in this case, 1 liter. So it's a very, very big chloroplast. But many authors, they don't care about volume. And so many times they just put it unit volume. And then it actually shows here a list of all the species that are contained into that compartment, which is, in this case, it's all the species because it is just one compartment. You can also have all the species. If you click there, you have a list of all of the species. These are chemical species. Gives you a very quick view of what they are. And by the way, the word fixed here is the same as clamped in virtual cell. The one, when it says reactions, it means that this is going to be an ODE and it's going to be created based on the reactions that this species enters in. And you have here the initial concentrations. If you go to the to the right, you'll see the current concentration, which is currently not a number. That's what NaN means, because we have not calculated anything. And the rate of change, and in how many reactions it enters. And in some cases, there could be a number of initial expressions, or even expressions for noise. I'm not going to talk about those today, but just to let you know they're here. Now, this is a table view. You can look at each particular metabolite or species. If you just double click, here it's aspartyl P. I don't know what that is, but we can see in a moment. This tells you that it's calculated based on reactions. So COPASI looks at all the reactions it takes part and builds the differential equation automatically from those. And there is an equivalent table for reactions. So if you click on reactions here, you get the table. If you expand this, you will have one by one. So here is the reactions have a name and they have a reaction equation. So if we highlight one of them, you will see the two things as well. So there's a name in there. The names have to be unique for the reactions, but they can be anything you want. And the reaction equation is basically the names of the species separated by pluses when there are several substrates or products. And then there's a character in between that shows whether it is reversible or non-reversible. You have an equals means that it is a reversible reaction. That means you have forward and backward fluxes. So there will be a net flux, but there is always forward and back fluxes in this case. This is normal chemistry notation. After the semicolon, you may ask, what is that? The semicolon is just to indicate that after this comes a list of substances that affect the rate of reaction, but they don't take part in the reaction. So all these three things here, AK1, lysine, and S-adenosylmethionine are substances that affect the rate of this reaction, but they don't take part. They're not converted, so they're not aspartate or aspartyl phosphate. And they actually do appear here, as you can see, S-adenosylmethionine and lysine and AK1. They're called modifiers. This is a term that comes from kinetics. Modifier is anything that changes the rate of a reaction that is not being transformed in the reaction. And that includes the enzyme, which is, in this case, actually this one here, AK1. But in this case, includes also two other substances. In this case, they are allosteric inhibitors, I believe. Now, these are all the names. There's a few other things underneath I will show later. But just to show that what annotation is important. Now, you may not know what aspartyl_P means. If you don't know, you can click here, the tab that says annotation. You might have noticed that tab exists at many different levels. So at the model level, there's an annotation. That's annotation about the model. In this case, it includes the email and the names of the authors of the model. It includes a link to the publication. It includes what characteristics of this model. So this model is in the biomodels database. It's part of a KEGG pathway. It's a version of something that is stored on gene ontology, and it's related to a species, biological species that has this taxonomy. Now, these numbers are identifiers in databases. They don't mean anything to you. But if you double click on them, you go to a URL, your browser will load the equivalent thing. So this is the biomodels page for this model. If I click the PubMed link, you go straight into PubMed. And from there, you could actually also get to the paper. So that's stored in the model. Now, these things exist in this model because the biomodels curators added them. They're not done automatically. So as a user, when you're building your models, you can add these things. It's a little tedious, but you basically select what is the resource. So for publications, it could be a PubMed ID, it could be an archive ID, it could be a DOI, and then you put the ID there. And then automatically later on, even other users that load your model, they can then double click and see what things are. This is quite important for molecules, for example, CGS. I don't know what that means. What is CGS? If I go into annotation, it tells me that it's this thing in the UniProt knowledge base. So if I double click that, it goes straight into UniProt and it tells me this is cystathionine gamma synthase 1. It's an enzyme. So now I know what CGS means. And here it also tells me the reaction. It has lots and lots of information about this molecule. So you would find out really what that molecule is. That's why annotations are powerful. So I'm going to leave the annotations. Just to mention that, of course, they exist also for reactions. They can exist for any single object in your models.
So Pedro,
also,
can I hop in for just 1 second and point out that I didn't get a chance to show you, but you can add all those annotations in VSOL models as well, but I just haven't shown you how to do it.
Exactly, and if this model, I mean, this model was loaded as an SPML from biomodels, you could also load it into Virtual Cell, and in Virtual Cell you can also see all of these annotations as well, and you can enter them too. So in this thing, both software are very compatible. Now, let me show the paper. I want to look at this paper because I want to now reproduce something. So I'm just going to load the version I have here on my hard drive, but I could just click there. There's the PDF. It's this paper, and what I'm going to do is I'm going to try and reproduce. Well, by the way, that's the pathway. If you want to look at it, you can look at it in detail, etc. But I am going to try and reproduce a figure here. I'm going to try and reproduce figure number 5, which is this one here. And in figure number 5, what they did was they calculated the steady state. They calculated how the steady state depends on the concentration of one of those clumped species, which in this case, it's actually an enzyme. And I can explain a little bit about what that means. But before doing that, we're going to first calculate the steady state of the native system. So I'm collapsing these things here just to give space. As I said, you have in the hierarchy, you have model. Incidentally, you can look at the mathematical model. And in the mathematical model, you can look at the differential equations. So here are the differential equations that COPASI will solve when you press the run button. And you did not want to type this by hand. These are all the parameters of the model. They are built from the actual kinetic expressions. And the kinetic expressions, you may have to enter them by hand, but if they're the classical ones like mass action, Michaelis-Menten, Hill equation, those they actually are available to be selected, and you just have to type the values of the parameters. Now, in this page, this is also important. Even if you don't use COPASI, you might want to come to COPASI just to do this. I know users who do that, which is you can save these equations in LaTeX format. And if you don't know what LaTeX format is, just ignore this. If you know what LaTeX is, this is very handy because you don't have to type all of the LaTeX symbols for all of this stuff. So if the reviewers of your paper insist that they want to see the full set of equations, as often I've seen, you can prepare the equations just by saving here, and now you select LaTeX. You could also save them as a PDF or as a PNG, which basically will just create an image of what you were seeing on the screen. But if you select tech, you can now save a file and call it, I don't know, my equations, my model, whatever you want, .tech. Save this, and now I'm going to show you. Again, if you don't know what tech is, I cannot explain, I'm afraid. It's too complicated. It's basically a system for typesetting and that you can write things. But if I just show you my equations here, here is the LaTeX file that contains, that I just saved. And as I said, you don't want to be typing this. These are, in this particular model, these are pretty complicated equations. Now, this is not a full LaTeX document. You would have to insert this into your document. You'd have to create, for example, an article document and just include this file. And this basically starts the math section, goes all the way down. So you can write your equations very neatly. You can produce a PDF and send it to the reviewers. This is often a pain in the backside to do otherwise. Any questions so far? Trying to see if there's any hand raises. Gamal, you have a question?
Yeah, so for sure, there is no geometry in COPASI. Everything is compartmental analysis.
For sure, there is no, well, there is geometry, but it's only topology, not really spatial geometry. There is topology, which is which compartments communicate with other compartments.
Correct.
Yes. So within a compartment, everything is has basically infinite diffusion coefficient. So everything is instantaneously equilibrated throughout the compartment. So there's no space dimension as in diffusion.
So because COPASI looks for me to be extremely useful code for physiologically based pharmacokinetic modeling.
Yes, you can absolutely do pharmacokinetic models with COPASI.
Okay, so the area under the curve is also calculated in COPASI.
You can calculate area under the curve. I'm pretty sure you can do it in virtual cell as well. I can show you that. The area under the curve is an integral.
Correct. Yeah, but it's very tough to do it if you want to do it every simulation.
Integrating. That's what COPASI is doing. Integrating. So it's there. It's available.
When you have a pharmaceutical or radiopharmaceutical, this is the other question I was going to ask you. Can you introduce a pseudo radioactive label into your equations?
Well, you can. You include another species. You distinguish them. In fact, I have done that in one of my models that I have published. You have to create the hot and the cold version.
Correct.
So different species, but yes, you can.
So I will send you an email directly so I can get your paper.
Yes. Okay. No problem.
Thank you.
So anyway, so I was showing you the mathematical model, but now I want to do something with my model, which is in this case calculate a steady state. So you go here underneath model. There is a section called tasks. These are all the operations you're going to do with COPASI. And the most basic one is steady state, which, as Les previously described, it's when you have no changes in concentrations. So in that case, you basically annul the differential equations. It becomes just a set of algebraic equations. And I'm going to explain here a little bit in this slide. This has an example model with 3 species with a lot of complicated kinetics. Doesn't matter, it's for that little pathway. And we calculate the, so just to highlight, you have the dA dt equal to this thing, but it's also equal to 0. And I'm also showing that sometimes we use this notation, which is a with a dot above. That means dA dt. That's easier to show you on the Jacobian there. But essentially, when we're considering steady state, you can look at just this part that is highlighted. That is, the right-hand side of the equations is equal to 0, right? So now this is a set of algebraic equations. And Newton, way back then, developed a method to solve these equations, which is essentially based here. These are vectors. So the vector xn plus 1 is closer to the steady state, or some people call it equilibrium. Because I'm from biochemistry, and chemistry, equilibrium has a very specific meaning. It's a special steady state, so I normally like to call it steady state. But the solution to that equation at n plus 1 is closer than the solution at n. So this is an iterative process. At each step, you update your guess solution from the previous guess solution by using the following. It's f is basically this function. You calculate this function for each of the 3 species, so that's a vector. And then that's multiplied by the inverse of the Jacobian. And what is the Jacobian matrix? The Jacobian matrix is a matrix that has the second order derivatives of or the first order derivatives of these functions. So it's the derivative of, in this first element, is the derivative of this function towards A. The second one is the derivative of this function toward B. The third is derivative of this function towards C, and on until you get to the last one, which is the derivative of this function towards C. You build this matrix called the Jacobian, and that's what is used there. The Jacobian is also important to, as we will see later, to look at the stability of the steady states, because the steady states may be stable and they may also be unstable. And we do an eigenvalue, eigenvector decomposition of this, and the eigenvalues need all to be negative. The real part of the eigenvalues need to be negative for the system to be stable. So I'm mentioning this because we can calculate those things in COPASI. I don't want to go through the theory very deeply. So if this is rather overwhelming from the mathematical point of view, just take it the following message. There is a method that COPASI uses to calculate the steady state, so we can get the set of concentrations that exist when the fluxes are 0. And once we do that, we can estimate whether that steady state is stable or is unstable. If it is unstable, then any perturbation will move the system away from it. If it's stable, if you apply a perturbation, then the system returns eventually to the steady state. So here in steady state, you have some parameters for the solution, which you may or may not ignore. By and large, you can ignore. I'm just going to point out this entry here says, I'm going to use the Newton method. Now, one thing you need to know about the Newton method is that it converges quadratically, but it doesn't always converge. So it sometimes fails. And when it fails, we use the other strategy, which Les also mentioned, which is what they use in virtual cell, which is we integrate the system a little bit. And in fact, in COPASI, we integrate a little bit. So if it's a stable steady state, you will get closer to it. And then we apply the Newton method again. And if that still fails, we integrate a little bit further and we try the Newton method again until this eventually converges, or until it does a certain predefined number of tries, and then it just basically gives up at some point. And sometimes it doesn't find any solution. So these are the two most important things. So I'm going to keep those, and for a steady state, all you need to do is to press the run button. And so it tries to find a steady state, and it found one now. And it's telling me the concentration of the species in that steady state. So that's the concentration of the species that are actually variables. There's more species, if you remember, but they were all constant. These are the variables, and it tells you their concentration, and it actually tells you their rate. Now, I told you a steady state is when the rate is equal to 0. So this is just so you can estimate the quality of the steady state. Is it a good steady state if everything is close to 0? So these numbers are all, the largest one is something 10 to the 16, 10 to the minus 16. So these are all pretty close to 0. It also gives you the transition time, which is basically just, it's actually the concentration divided by the flux that passes through it. It's a measure of how fast that variable is. So this variable here is very slow. If you perturb it, it takes a long time to relax. This variable is very fast. If you perturb it, it takes a very short time to relax. But that's not the time to relax, but it's proportional to it. Now you can also look at the reactions in this tab, and now that gives you the flux of the reactions. And by definition, in a steady state, the reactions that don't have any branch out, they will have the same flux. And in this case, everything is branched, so you don't see that they add up. So everything that comes into a node is equal to the sum of what goes out in that node. That's why the concentrations the changes are 0. Now you can look at stability. This will tell you if your steady state is stable or not. And this tab is really for those who don't want to think about the mathematics. All you need to do is to read what it says here in summary. It says the steady state is asymptotically stable. So you know this is a stable steady state. It also says that there's some oscillations in the vicinity of the steady state, probably. Now, if you're mathematical, you know that this is asymptotically stable because the eigenvalues are all, the real part is all negative. Now you can look at the eigenvalues here in the Jacobian. That's the actual Jacobian matrix that I showed you, the values for the Jacobian matrix. But you have here the eigenvalues, and you can see they're sorted. The top one is always the largest real part, and that is negative. And all the others are even further from 0. They're even larger, they're more negative. So they're smaller. So everything is stable. That's how COPASI can say this. But as I said, if you don't know about the maths, just check this part, because this will tell you what you want. So we calculated one steady state and we have the result, but that's not what you normally want to do. Normally you want to see the dependency of things when you change parameters. So if you go back to the paper, let me pull the paper again. In this figure, what they did was they changed the concentration of one enzyme. It's actually an enzyme that consumes lysine, and they see what happens to the fluxes of 3 reactions and what happens to the concentrations of some species. So we're going to do the same. So if you were to read the details of that, you find out that they changed LKR between 0 and 30. And that's what we're going to do. So how can we do that? Well, we could do it manually. by going to the model and looking for the species LKR and changing it from 0 to 0.1 and run again and do this back and forth. That's very tedious. You don't want to do that. So what we want to do is you want to scan the parameter, which is LKR. And let me point out that even though it's a species, it's fixed, and therefore it's a parameter. This is an enzyme, and in their model, they're assuming that the enzyme concentration isn't changing, it's fixed. However, they're going to change it, and for each value, they're going to ask, well, if it had this value, what would be the steady state? And if it had that value, what would be the steady state? And that's what we call a parameter scan. So that's the operation called parameter scan here. And I'm going to get into it, but in the meantime, I'm going to see if there's any questions.
I have a question. I was wondering, what's that kind of oscillation number?
The oscillation, let me get back to that. So the oscillation, it says that there's probably some oscillations around the steady state. And that comes from the fact that there are complex eigenvalues. So if you go back to the Jacobian, the eigenvalues of the Jacobian could be complex numbers. The first one is not complex. It has a 0 value on the imaginary part. That's the real part, that's the imaginary part. Neither is the second one, but you see the third and fourth are actually a complex conjugate. They have the same real part and they have just symmetric values for the imaginary part. And that's where COPASI knows that because of the existence of these two eigenvalues, there are some oscillations. They probably are very damped. It depends a lot on the sign of the imaginary part, and this one is pretty small. So they're probably just one bump, which is like an oscillation that has very, very high damping. And in fact, it even tells you what frequency that would be corresponding to. So that's what the oscillatory part means. In this case, this model is not very important. There will be another one that I may not have time to get to, given that I was stolen some time, that I would show that. Okay, so I'm going to go do a parameter scan. So in parameter scan, in COPASI, there's a number of things that can be done in parameter scan. And the first one is to say, this is basically a way of repeating a task several times. And there's many tasks you can repeat. These are all the different ones. You can do this for many things, including parameter estimations. Later on, you will see why that might be useful. In this case, we want to do a steady state, because that's what that figure did. Calculates the steady state at different values of that species LKR. So I've decided the task. Now I need to say I want to scan one parameter. So I can have an option here. I could either scan a parameter, or I could just sample it from a random distribution. So I could do random values rather than regular values. I could also just repeat the steady state, but repeating the steady state is not useful because you should get the same number over and over again. This will be more useful for the stochastic simulations. But in this case, I'm going to scan, and I need to say I want to scan something. What is the something? I press the create button, and now I have all the options of what I can choose. Now I want to choose a concentration of a species. So I go to species, and in fact, I want to change the initial concentration of a species. I could change the particle numbers too, but this is our large concentrations. I don't care about particle numbers in this case. Now I have to find which one it is. It's LKR. I select, say OK, and here I have. I'm going to scan LKR for a certain number of intervals between some value and some value. Now I don't want to do it 0 and 0 because that's nothing. Remember, the figure said it was from 0 to 30. So that's what I'm going to do. I'm going to do 0, and I'm going to write 30. And I'm going to keep 10 values, but I can change this. This is how many intervals I have between 0 and 30. So it's actually going to be 11 values, not 10, because the intervals are bounded on both sides. So all I have to do now is run, and this would do it, except that I don't have any output to look at. And if I go and look in the species, it will show me just the steady state concentration of the last one I calculated. Now I want to reproduce the figure. I want to reproduce this figure, which is actually fluxes. So what do? I go back to parameter scan, and I select the output assistant, this button here at the bottom. The output assistant gives me a selection of plots that are more or less what you might want to do when you do a scan. There are ways of creating other plots. I will show, or maybe we can talk about later, how to create other plots. There's also one of the video tutorials shows you how to do arbitrary plots of different kinds. In this case, I want a scan of the fluxes because I want to see the reaction fluxes. So this is going to show me the reaction fluxes on the y-axis and the parameter I'm scanning on the x-axis, which is exactly what they have in this figure. They have the thing they scanned in the x-axis and they have the fluxes in the y-axis. So I just select that and I press the button create. Now what this did is that it created something here in another part of COPASI. So you have model, you have tasks, and you have now another thing called output specifications. And in there you have plots and reports. And now you have one plot, which is this one I just created. This was created automatically. I'm not going to change it, but you could change it here. And that's what that tutorial will tell you. Go back to my tasks, parameter scan. And now if I run this again, a window will be created with the plot of the various steady states. And there it is. Now, this is not what they have, the figure they have, because the figure they have is specific for 3 fluxes, and this one is showing all the fluxes. So I need to choose. This is a legend, tells you which color is what, but it's also a toggle. So you can have things on and off. Because there are too many of them, I'm going to press the button that says hide all. And now I'm going to look for the particular fluxes that are shown here. And the fluxes that are shown here are the fluxes, and I've studied this paper before, so I can go quickly. I can tell you which ones they are. They are the lysyl aminosyl tRNA synthase flux. That's the flux lysine to protein, that one. The threonine aminosyl tRNA synthase, the flux from threonine to protein. And then they have the VLKR, which is a different one that I forgot which one it was. So this one. So there you are. You have the same picture in COPASI that they have produced in that paper. That's the same exact picture. So now you wanted to produce a figure from this. You have a few options. You can save the image. You can save it in various formats. You can save a PDF, you can save a PNG, or you can save an SVG file. SVG is a vector format that you can resize with high quality. It goes into things such as Adobe Illustrator or Inkscape. We could do that. We could create a PDF straight from here. That is not quality. It's not publication quality. So it's good to share between your colleagues, etc., but it's not what you want to put in a publication. You can also save the data. This will save a text file that contains all the data, and then you can load it into a graphics program, then produce a nice, pretty picture of the whole thing. So I would call it my Fig 1 or Fig 5a, and save it, and you don't even need to, I mean, these are tab separated files, so I'm going to call it TSV, and then you could load that into Excel, and you could use that to make a figure or even some better program. Any questions?
Yeah, I have a question. Is there a possibility to, for example, add an inhibitor at a certain time point? So you
Yes.
run your model, then add your inhibitor and then run it again, or like keep on running it?
Yes. So if you want to add that, so you can do that, but that's for a time course. For a steady state, you have to calculate the steady state. This is time infinity. You don't know when it happens. So when you have those things, you cannot really easily calculate a steady state. I mean, you can, but it's not the best way, because the event that you're talking about is going to happen at a certain time, and you could hit the steady state before that time, in which case the event wouldn't happen, or you could hit it afterwards, in which case the event would happen and the outcomes would be different. So be careful with that kind of experiment. Is usually for a time course. But indeed, you can do that. So let me show you a time course. So now we want to do a time course. So I'm no longer going to the steady state, and I'm no longer going to the parameter scan. I'm going to the time course. Here is just like in virtual cell, you say how long you want it for, and how many output intervals. And this is for the integrator. You also have a choice of integrators, but just leave it to the default for now. So let's say we want to do 100 seconds. Press the run button, and it would do 100 seconds. If you expand this, you actually have the results here. But again, this is not useful unless you want to save it and take it somewhere else. What you want is a plot of the concentrations versus time. So again, to the output assistant, you can choose concentrations and volumes along time. You create that and you run again, and now you have a plot of the time course. Now, let's say you want to do, and let's look at, say, lysine, because I'm going to reproduce what you said. So let's say we have lysine, oops, that's the concentration along time. So now let's say that you wanted to add, at time 60, you wanted to add a finite concentration of that enzyme that I mentioned, which in this case is 0 at the beginning. So if you go back to the model, that LKR is 0. But now let's say that at time 60, you inject somehow that enzyme into the system. So you can do that by creating something in your model called an event, which you come here, and then you create a new one. So just double click there, it says new, double click here, and you can even call it something, addition of LKR, or you could just call it A or B or whatever you want, event 1, anything. And now you're going to have to define a trigger expression, that is what causes the event. In this case, it's time. So we're going to select time, model time, and we're going to say this has to be a logic expression, has to have a true or false value. And I'm going to say time bigger than 60, which is false until time hits 60, and infinitesimally after time is 60 becomes true. And the event happens when this condition goes from false to true. So essentially it'll happen infinitesimally after time 60. And then what do you want to do? That's the target. We want to change the concentration of LKR. So we go here and we change the concentration, species, change the concentration of LKR. And let's say we want to make it 20. So we just write the value 20 there. So at time, this means at time 60, set LKR to 20. So now let's go back and run the time course. So there you are, there it goes. And at time 20, you see there's a discontinuity here. At time 20, this happened and you changed the LKR enzyme. So that did an effect on your experiment. And you can have an arbitrary number of these events programmed. So you can program a complex experiment that way. The events are also very useful for something else that I will not have time to show, but, or maybe I won't have probably time to show. Actually, I may jump into that. Are there any other questions right now before I move on to another model? Just to say that you can scan other things. You can add other scan objects. So you could scan, you can do a 2-dimensional scan. You can add another parameter, or you can add another 5 or 6 parameters. The problem is that once you add a lot of them, you have the curse of dimensionality, because now it becomes a product of all of those simulations. You can very quickly run out of time to run all the simulations, and you could even run out of space to store all the data in your hard drive. So, because if you're going to do 10 simulations of 10 things, that's 10 to the 10. There's a lot of data produced. So be careful when you create multiple scans. Things can easily get out of hand. Okay, so I'm going to load another model from biomodels.
Petra, I have a question.
Yes.
When you were defining events, there was an option to define the priority.
Yeah.
What is it about?
Okay, so in the unlikely event, or in the unlikely condition that 2 events get triggered at the same time, then the one that goes first may affect the second. So for that, we can assign a priority to this event, just so that if another event happens, COPASI will pick the one that has the highest priority first. Okay. Hopefully no event will happen, because the theory about this is actually falls into a part of mathematics that is not fully worked out, called hybrid systems. You have a combination of continuous and discrete. And when you have discrete events like this, you have this problem that if one affects the other, which one comes first? And that actually hits a lot of areas in engineering. For example, design of CPUs, CPU code, that can happen in CPUs. They're called race conditions. And how to solve those is not trivial. And the maths behind it is also not solved. So the way out of that, defined by the SVML community, was to give priorities. The modeler decides that if they happen to, two events happen exactly at the same time, then the one with the highest priority goes first. But in fact, there is no good theory to pick which one should go first. And the order of them would change the outcome, potentially. But I have to say that's a very rare thing. I mean, it's not so simple to create a model where that condition happens. So I'm just going to borrow the 10 minutes that were stolen from me from the next thing, and show you just one more example, just to show you how to do another way of using events that is very useful. So now I'm going to load another model from biomodels. This one is number 10. And it's a very famous model of the MAP kinase cascade that oscillates. So I'm just going to write 10. I'm going to load, and I'm also going to load the PDF. Oh, COPASI is saying I didn't save my file. Normally you would want to save your work, but I mean, in this case, I've just been doing demonstrations, so I'm going to discard it. And the new model is loaded. And let me just show you what that paper, I have it here too, but you can again get to it the same way that I mentioned. I think I have it, I think I put it on the shared drive as well. So it's paper by Boris Kolodenko from 2000 that has this MAP kinase cascade that actually includes an inhibition of the activation signal by the MAPK-PP, the ERK, doubly phosphorylated ERK, and that causes oscillation in some conditions. So that model, again, you can go and do everything, look at the annotations, etc. I'm going to leave that alone, and I'm going to just show you the model running like they have it in their paper. So this figure, they integrated for 0 to 150. So we want to run 150, and I want much more than 100 intervals. Let's say 1,000, probably better. Again, I want to see an output, so I'm going to create the plot, and I want to look at the concentrations. And so now when I run, those are my concentrations, but I suspect that in the model, this is minutes exactly. So this is a usual thing. People put figures in their papers that are in minute time scale, but then their models are in seconds. So you have to convert things by 60, right? So let me just do, oh, well, let's do 6,000, which is not exactly, or 8,000, maybe the correct value. There we have it. The figure is similar to the figure they have, except that they're only showing, I think, 2 species. I'm not sure which one. The MAP kinase. So it's just the phosphorylated and non-phosphorylated versions of the MAPK, which is ERK, and phosphorylated ERK and doubly phosphorylated ERK. That's the figure they have, more or less. Now, this model is oscillatory. So if I go to look for a steady state, I will maybe not find a steady state, or if I'm lucky, I find an unstable steady state, which most oscillations, these so-called limit cycles, they have an unstable steady state inside them. It's like the oscillation is a cycle, and in the middle, there is an unstable steady state. And I think COPASI is going to find it. So it is indeed found a steady state. And if you look at the stability, it says this steady state is unstable. So, and why is it unstable? Because the largest real part of an eigenvalue is a positive number. That means if you perturb it, it goes away out of it. And in fact, it will go into the limit cycle. And that's why you never see them stable steady state. You only see what the system converges to when it's perturbed out of that steady state, which in this case is the oscillations. So this is just to show you that you could calculate a steady state. Sometimes there may be an unstable steady state, but you won't see it. COPASI might not be able to find it. But in this case, it happened so that it did. Now, I want to measure the period of these oscillations. Let me run the oscillations again. I want to measure the period. I want to know what is the period of these oscillations. How long does it take to go from the peak of this to the peak of that? This amount of time, that's the period. Okay, so how do I do that? Well, I can do that with events. What I'm going to do is I'm going to create an event that detects the peak of this oscillation. Now, if you think about it, what happens there at the top is that the rate of change of this species is positive here. It's increasing, right? And it's negative there. It's decreasing. So it's actually 0 at the very top. So I can create an event that gets triggered when this changes from positive to negative. Remember, the events are triggered when a logical condition becomes true, goes from false to true. So I'm going to create an event that does that. But before I do it, I need 2 variables, extra variables that are just going to be needed to calculate the period. I need one of them to tell me what was the time of the previous peak. And then I need one that measures the period, which is the current time minus the time of the previous peak. So I need to create those 2 things in the model, and I create them in these so-called global quantities. First one, I'm just going to call it previous time. And the other one, I'm just going to call it period, which is really what we want to measure. And leave them at 0 for now. Now I create an event. And that event is going to be triggered by when the rate of change of ERK, right? So it's a species, and it's the transient concentration, and it's ERK2. When that, but it's not the, I made a mistake. It's not the species concentration. Let's get rid of this. It's the rate of change of that species. So you see, you have transient concentrations, but you also have rates. And they can come in concentration units or in particle numbers. Forget particle numbers, they're only good for stochastic simulations. You want concentration. And that's this here, dERK2 dt. That's what I want. And I want that to be negative. Now, when it's in this part, this statement is false because it's actually positive. And when it hits the top, it becomes true. And so that's when the event happens. Now on that event, I'm going to capture the value of time in my variable previous. You will see why in a moment. And so that variable is going to, I'm going to assign the value of the current time, which I get again from here, current time. And I also want to create a period. And the period is going to be the current time minus the previous. Period is the variable I want to affect. And I want it to be the previous time. Now you'll get a little confused, perhaps. It's going to be the previous time minus, sorry, the other way around. It's the current time minus the previous time. Otherwise, I get a negative number. So it's the current time, and I put a minus sign, minus the previous. Now, you're saying, well, so what about the previous time? Well, the previous time was assigned in the previous event. Remember, there's several oscillations. So at the beginning, the previous time is 0. So the first period will be a number we don't care about, because we're going to run this for more than one oscillation. This will get updated at every time the event is triggered, which is at every peak of this variable. So by the time we get here, we forgot it, the COPASI has forgotten the values before, but that's okay, because in fact, the first oscillation, it's not the final period, it's still stabilizing. So it's better here. So we're going to use the value of period here. And so that is the current time minus the previous time. Now the previous time was assigned the previous time that I've moved here. And you may say, no, but you just assigned it before. No, when there is an event everything that happens here is assigned at the same time. There's no order for these. These are all at the same time. They're all updated together. So when I assign the value for period, previous time still has the value of the previous time, not the one that was just assigned. This one is only going to be available for the next event. I suspect there will be questions. I'll take them at the very end because we're really running out of time. I just wanted to show this working. So that's my event that's going to be detecting that. And I'm going to calculate the period out of this. Now, because 0 is hard to find, I'm going to actually, rather than 0, going to put a very small value, 1e minus 12. And that numerically is more stable, easier to find that value. So now I just run my time course. Okay, so I run my time course, and now I can go and look at what is the value of period. And there it is, the value of period is 1,299 seconds. That's the period of these oscillations. Any questions? If there are no questions, I'll take one more second and I'll show you how to change that period. Let's change some model parameter and see if that affects the period. So I know one that does. I'll get to the questions in a second. And it's the inhibition constant from that feedback loop that you saw before. And if I change that value, it's going to change the period. Now I want an output that includes my period, and I'm going to get it here. I forgot one thing. Let me stop this. I don't want the output while the simulation is going. I just want the final value. While this is calculating, and I'm now going to, oh, it didn't include it here. I don't have the period here. Anyone that wants to ask a question, go ahead. I'll be just adding one thing to the plot, but I can answer your question.
Okay, this is Kaustubh. I have one question. Suppose you want to record only the instant at which the peak is reached. How will you record that and plot it separately?
That actually is what I did with that variable previous time. It could be called peak. Yes, you can do that, and you can plot that. So I'll show you the value of, actually I can show you that straight away before I can show this thing that I was going to show. So when you run the time course, I have to add that variable. Because I had created this before, I'm going to need to add a new curve to this, which is my two variables. So now if I run again, I now have also the period and the previous time. Previous time is really the times when it happens. So when it happens at time 300, at time 1775, at time 2928, at time 4304. You could output this, so you could have these numbers output. So you have exactly the times of the peaks. Now, if I show you the period is first very small because this is, remember, the first one doesn't count, but it gets high. That's the first oscillation, and then it stabilizes. And then it's the same. If I did the longer time, let's do 80,000, we do 10 times more. So if I'm now running this, you see the period is now stabilized, and it's always the same, even though I'm collecting it over and over. If I show you the actual time course, that's a big time course, but the period is, the period is still the same. Because in the beginning, there's like a little bump here, that's the perturbation of the initial conditions, then it stabilizes. So yes, you can calculate the time. You basically, you just store it in a variable. That's what I did here. This variable previous time, it's actually the time of the oscillation. But I called it previous time because in my calculation, I'm using it as the time of the previous oscillation. So I'm going to end here because we've taken a chunk out of the rest.